So in this video, we're going to dig deeper into the H8-16 card. We're going to take some of the work we've done previously to understand the card. We're going to do a bit of reverse engineering on the card, identify what columns of RAM chips are data 7 and data 0, etc., and kind of really begin to bring all this together. What you're looking at now is a diagram I've drawn up that kind of looks at the card, captures the chip locations, the actual TTL IC numbers, pinouts for things, the bank 0, 1, 2, 3 designations, etc. Anyhow, I'm going to kind of dig into how I determined some of the details here on the card. So as I continue to investigate the H8-16 RAM card, I've drawn up this page that you see here, and this page captures device numbers a little bit easier to read. It's got the TTL equivalents of these devices here, the part numbers, some notes on the 4104 RAMs the board uses, and some of the things we've been able to deduce. I'm calling this bottom row here block 0. It lives in that address space. Block 1, block 2, and block 3. These are the most significant byte of the address space represented here. So trying to figure out whether data 8 is on this side or this side. This is the process I went through, and I'll duplicate it here. I've removed one RAM chip here down there, and that should be out of this block in the address space 020 to 037. So I shouldn't be able to write to this address space. Now that empty socket's either going to return a 1 or a 0, most likely a 1 consistently. So with that RAM chip removed, it's always harder to get the card in when the camera is running, and I'm not sure why. There it is. The system will come up and operate with that chip removed. Bring the power up. And what I'm going to do now is I'm going to set the address space to where I believe this block of RAM lives with the missing chip, and that's 020 000. So let's go in and set our... So we should now be at the first address of that block of RAM, and now I'm going to alter data, and I'm going to write in a 000, and then I'm going to write a 001 to the next address, a 020 to the next address. I think I screwed that up. Oh, we're already seeing a trend here. We do this again. I'm going to put 000 into this address space, and then 001 in the next byte, and then 002 into the next byte, 004. If you see what I'm doing here, I'm shifting a 1 across. So then we go to 010, 020, 040, 100, and 200. And what that should do is basically start out with all zeros, and we can already see that the D8 bit or D7 bit, if it's data 0 to data 7, the data 7 bit here is 1. We should expect to find a 001 in this address, and we again find a 201, which tells me that data 8 bit or data 7 bit, let me say it correctly, is high. And what we can see here is that 1 bit seems to always be stuck high as I walk the single 1 across. And that appears to be correct. So we've determined really that data 7 we've confirmed that data 7 appears to be in this column. I'm going to go ahead and pull out the data, what I believe to be the data 0 bit. I'm making an assumption these are in logical order, data 7, 6, 5, 4, 3, 2, 1, 0. The layout of the board may have dictated that that's not true, but we'll work our way through here and see what we've got. So let me pull the card back out. And I'm going to transfer one of the RAM chips over. Empty one socket and put that RAM into a different socket. So what we've done here is taken the RAM from this socket in this bank, it's now an empty socket, and transplanted it over here. And the assumption is this is the data 0 bit here. Now, nothing guarantees that. I swap this thing out all the time. With the camera off, and it's easier. System should still come up, and we'll do the exact same experiment. So we'll set the memory address to 020000, and then we're going to alter memory, and we're going to write in a 000, 001, 020. Oops, I did that wrong again. 001, 002, 004, 010, 020, 040, 100, and 200. And as we step back through here, oh, I'm going the wrong direction. Let me get back to the beginning of the block. We can see where we expected there to be all zeros. There's a 1 in the least significant bit, which tends to say the left-hand column of chips is data 0. We find a 1 where we expected a 1. We expect to find a 2 here, and instead we're finding a 3, so both data 0 and data 1 are high. We expect to find a 4 here, 0, 1. That's interesting. That's not the bit pattern I would have expected to see. 1, 2, 1, 6. That should have been a 0, 0, 0, a 0, 0, 1, a 0, 1, 0, when it's actually a 0, or a 0, gosh. 0, 0, I know what I'm trying to say. This should be a 0, 0, 0, and it's not. There should be a 0, 0, 1, and it is. There should be a 0, 0, 2, and it's actually a 3, so we know that the data 1 bit is set, and data 0 appears to be a 1, which we can tell. There should have been a 0, 0, 4. It ends up a 5 because, again, that least significant bit and the data stream is floating, is being pulled to a 1. This should be a 0, 1, 0. I must have typed something wrong here. 0, 2, 0. Let's go back and alter this to be a 0, 2, 0. Alter. Alter 0, 2, 0. There it is. Anyhow, I'm confusing things here with this, but what I've been able to determine at this point is data 0 is this column over here. So let me turn the power off. And we're going to confuse this up a bit more, but I want to make sure that the order really is what I think it should be. Of course, can't get him back in the socket. You know, I'm just not as good at explaining this stuff as I used to be, apparently. Apologies for Rosie in the background. So I've pulled out 2 RAM chips at this point. This should be data 6, and this should be data 3. So the bit weights is going to be 0, 2, 4, 8, 16, 24, and 32. Those 2 bits should be stuck a 1 no matter what we write into that space. And if those make sense, then I'm going to be confident that I have this right. 0, 2, 0, 0, 0, 0. Alter data 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 4, 0, 1, 0, 0, 2, 0, 0, 4, 0, 1, 0, 0, and 4, 0, 0. Now we expected there to be 0, 0, 0 here, and we can see that the 3rd bit is set in each one. So data 0, 1, data 2 is high, which is what I believe that socket there is. And again, data 6 is high, which will give us the 4, 4 pattern. And it went the wrong direction. That's consistent. We wrote the 1. That's consistent where we wrote the 2. That would be, because it's pulled high, we see what appears to be the right data even though it isn't. Yeah, I'm confident at this point that the board is laid out logically. Rosie, I'm busy. So I'm pretty confident this is data 8, 7, 6, 5, 4, 3, 2, and 1. We know the address blocks. This is in the 020, 000 to 037, 377 space. So we know the blocks. We know where the bits are. From there, hopefully I can start to decode the memory test failures with confidence that I'm looking at potentially the right chips on the board. So a couple other things to note here, just because I find them curious. Without the upper bank or this bank here installed, the system doesn't run. So the system is expecting to find a RAM in this 040 to 077 address space. It doesn't seem to mind if these are there or not. So I find that curious that it's expecting 16K. That may make sense. There's no guarantee this ROM is an original ROM. I don't know if I can actually get the CPU card out enough to see the ROM. Something else I wanted to look at here was the part number on that ROM on the processor card, to see if I can determine what version of PAM this is. And what looks to be the HeathKit number is a 444-13. Oops, bumped the table. ROM, I'm guessing 444-13. I found some notes online that I have modified. I've actually kind of stolen them. The web page hadn't been updated in well over a decade, and I've grabbed his contents and just produced a quick Word document that I'm expanding upon as I work through space. So 444-60 was the H8-9 PAM Go ROM replacement, according to this. So that's not what we have. Did I say that was 444-13? So the Heath part number 444-13 is the original PAM8 monitor. So that's good to know. We knew it was a PAM monitor based on looking at those initial 16 bytes in it. I now know it's an original PAM8. That can kind of give me some expectations about how things should work here. So I need to go find if there's any documentation on PAM8, especially technical notes, just so I understand it better. Anyhow, I'll wrap this up. This will just be a quick video on a little bit of, quote, reverse engineering. Kind of being logical and determining things. I'll retake a peek at this sheet here that I've drawn up. The X-ray view of the board is, there were some PDFs attached up on the Google site, the Google Group site, and on there I grabbed that PDF, grabbed it out into Paint, and just started to kind of add documentation. So you can see I've written in the chip numbers here. I think I mentioned this before, the actual TTL device numbers. The little blocks of green here represent numbers that are on the silk screen. So this is the 852197-1 that's on the board I've got. It says H8-16 up here, 16K static RAM, and a little bit of notes around this dip switch that's used to enable the board and to set the base address. So I tend to go through and develop documentation like this as I go through a system. I'm going to go in and add notes about data 7 to data 0 and the block numbers here, address space, and this will just become more and more useful as I move forward. So anyhow, I'll end here and we'll talk soon. Bye. Well, I hope this video was somewhat entertaining and you've learned something. I'm still looking for documentation on the H8-16 card. There's H8-16 documentation out there, but that card differs. Some of the parts that are used in various IC locations are different. At least 2 of them are swapped. Anyhow, I'm still digging for documentation for the H8-16, and I'll continue my effort here to reverse engineer out the card and hopefully fix it.